All right, so I'd like to introduce Ammar Latif from Cisco Systems. Now, he's going to talk about the other really important aspect of IP video and audio, and that's how do we connect all these great sources and great receivers together. And I think you'll really enjoy his presentation. He's doing a great job. Thank you.
Perfect. Thanks, Wes. Hi, good morning, everyone. All right, so the essence of this presentation, if you are a broadcasting engineer, this is a topic that you need to realize as you are going through building these fabrics. And if you are an IT engineer going into the media space, also is relevant to you because you want to understand how to build the fabric for this media workflow. So if we step, so the previous presentation was going deep into AES 67 and PTP and the synchronization. Let's step back a bit and say, what do I need to do from an Ethernet? I'm building how do I interconnect these endpoints together? What considerations do I need to take in, keep in mind as I am building this infrastructure? I'm being told always that in the past, the first thing that goes into the building is an SDI router. They put the first thing is the SDI router, and then they start connecting everything else. So probably we'll need to do the same thing here. Now, you are involved in this project, what considerations you will have? So, very simple. You might say, well, why don't I just use an Ethernet switch, just plug everything to it, and we'll be done. Which is true. You could do that. It really depends on your scale. So, typically, in a lab environment, you will probably start with something like this. But let's see, if you want to build a facility or even a truck, what considerations do we have? And there, we're keeping it simple. It doesn't need to be complicated, but what are these considerations? So, from a requirement perspective, right? We're building the infrastructure. We're building the infrastructure for this SIMT 2110. What are the requirements? And please, let me know if you disagree with some of this. Main thing is, let's try to stick to off-the-shelf switches, meaning not purpose-built switches. That's one of the requirements that we are assuming in here, not purpose-built switches, off-the-shelf data center switches that are being used in IT. I want to use them here. Why? I want to benefit from the price point. But I want to make it in a way that is deterministic. Meaning, we know, we always think Ethernet is like a mailbox. You drop the packet in, and somehow it gets there, but I don't know how. So how do I make it deterministic? So, COT switches, deterministic. I want endpoint synchronization with PTP. So we need to address that. We need to address high availability. How do I make sure if I have a part of the system down that I maintain my operation? Network security and scalability. So that's basically whether I want to start small and I start to scale out, or I want to start large. I want to build a full studio. So basically, these are the requirements that we will basically match against the infrastructure as we go through the presentation. How do I achieve these requirements? Let's start from the bottom up. So from a network switch perspective, these switches that I'm showing on the screen are basically the typical two form factors you will be facing. So it's either a modular chassis, which very looks like an SDI switch. Size-wise, it comes like four slots, and this is not necessarily only from Cisco. These are form factors that are known in the Ethernet switch industry. So modular switches, line cards, etc. Or you have a 1RU, 2RU form factor. We call them top of racks. The main difference between these two is, of course, density, but they would have high two supervisors, just like probably an SDI router, two supervisors. So, in both cases, assume that they are non-oversubscribed. These switches, whether these top of racks or these modular chassis, they are non-oversubscribed by nature. Meaning the packet comes in, you are absolutely confirmed that it will be non-blocking on the way out, within the switch. So what considerations do I have for this? What considerations do I, which one do I choose? And the idea is basically you will be driven by the endpoints. You need to start by the endpoints. What do I connect into here? And we'll have a slide on that. So these port speeds are basically, will connect to the endpoints. And they range from 1 gig, 10 gig, 40 gig, and 100 gig. And basically, again, the endpoints that connects drives the form factor. So this is like, again, starting from the bottom up, these are the switches that you start with, and you are now starting to build a system. Why are they non-blocking? A typical top-of-rack would look like this. So why is it non-blocking? Because typically they are built within a single ASIC or maybe a couple of ASICs. This is inside the switch, or just, blowing it up, and then this is inside the switch. So basically all the ports connect to a switch, ASIC, and maybe a couple of ASICs, and then they are in nature non-blocking. So now, we talked about endpoints. Two types of endpoints that we are seeing increasingly. One is native IP support. So maybe cameras that are native IP. Or playout systems, servers that connect directly into IP, and they support 2110. For these ones, it's easy. You need to understand what is the port connectivity. 10 gig, they typically are there. 10 gig, 25 gig, 40 gig, depending on how many flows they are trying to put into a port. But you still have legacy SDI endpoints, and that's basically where we need these IP gateways. And this is basically offered by, we're showing here in the room, is basically the IP gateways for connecting, of course, the legacy. Typically, the IP gateways are multiple SDI in, and then you have IP out in A/B. A/B paths, two paths basically. So your consideration is basically what port speeds is needed here, and also this A/B path, and we'll discuss about availability. Now remember, what we see here is basically typically 10 gig, 40 gig. We are starting increasingly to see a move to 25 gig, 50 gig, and 100 gig. So this is what we see. We see a lot of IPGs that are 10 gig, but we are seeing a lot of IPGs and endpoints that are 25, 50 gig, and 100 gig. Why? Because the 25, 50, and 100 gig is a family by itself. Okay? Because you can take the 100 gig and basically break it up into 2 by 50 or by 4 by 25. We have not seen 400 gig yet, but basically the next step from 100 gig is 400 gig. And we will talk about that. So 400 gig is basically the next speed coming out. I think I have a slide on, we can talk about 400 gig. If not, we can talk about it a bit at the end. So now we have, again, these endpoints. And so how do I deploy them? How do I build the fabric? The first one is, let me put a single chassis. And build my facility into a single chassis. So I'm showing here a modular chassis, or even a baby spine, we call it. 2RU high density. Let me home run everything to it. And we are very familiar with that. It's like an SDI router, right? We home run everything to it. All endpoints are connected to the single chassis. This is simple. We are comfortable with. The challenge is that it's a large failure domain. If the system fails, your half of your bandwidth is down. That's number one. So large failure domain. Number two, you have to home run. So basically cabling issues. And the other is, if you need to add capacity to this, you have to forklift. You have to replace the chassis and put a larger chassis in place. Let's say you start with 8 slots, you need to go to 16 slots, forklift. Remove the 8, put 16. Which is fine. Again, these are the considerations in your mind. Number two is basically this Spineleaf architecture we call it. So what's a Spineleaf architecture? The same top of racks that we discussed, where endpoints connect to, and then the leaves or the top of racks that we discussed goes into a spine. What is the consideration here? Why would you go here? It scales nicely, it scales horizontally. You need more capacity, you basically add more leaves. That's number one. And your top of racks are closer to the endpoints. So what does that save you? That saves you on cabling, but also it saves you on cost of optics. Because if your endpoint is close to the leaf, you see the optic cost when it comes short range or long range, very expensive. But if it's within 3 meters, 5 meters, very cheap. So consideration is basically, this is the benefit of Spineleaf architecture, is that you're closer to the destinations. It's distributed, your failure domain is small. If you leave a top of rack here, you have the rest of the bandwidth available. If you lose a spine, you at least have half of your bandwidth available. So you continue to function, you have a failure, but your failure domain is smaller. Okay? But it comes at a, what's the cons of it, right? This is all good. What's the cons? Is that now you have to manage multiple endpoints. And then, what's the other thing? How do I make it deterministic? Remember we said deterministic? Packet in, you want to make sure the packet is in, goes out. So that's the consideration, is basically you need somehow to do bandwidth management in this. Think of these are like tie lines in the SDI world. Okay? So we'll talk about how do we do this. And what we see. What we see in the deployments today, we see these deployments. OB truck, we see a single chassis. Easier because again, simple, you put it in space, it saves you space. We see a single modular. To be honest, in the rest of the deployments, what we see from a Cisco perspective and with our customers is mostly spine leaf. They might start small, couple of leaves maybe, but it is a spine leaf architecture because it scales. Now, you don't need to, again, these are again considerations in your mind as you're starting to build this system together. So, this slide, I have it for broadcast engineers that most of us are here. Basically, what we are trying to call out is the difference between SDI world and IP world. There's a lot of confusion, and I hope this slide clarifies it. Who sets up the path between the source and the destination? In an SDI world, which is to the left, the management system communicates with the SDI router to set up the path. And if you need point to multipoint, you do the same thing. In an IP world, this connection path is set using IGMP. Okay? What does that mean? That means the control system does not necessarily communicate for setup, path setup with the fabric. It is going through destination, and the destination sets up IGMP. Now, IGMP, if you want to look at it, is the gateway. It's our doors into the IP world. Now, if you want to do bandwidth, if you want to do broadcast controller communicating with the fabric to set up the path, it looks nice on paper, very nice science project. But in reality, again, IGMP is the gateway, is the doors to IP. All the setup here is IGMP based. All the deployments that we have is IGMP, and there is a reason for it. Standards, you are working with the standards. You continue building on what IP developed. And if you like, we can discuss it later on. Happy to discuss this topic. But again, there's a big difference between the IP world and when it comes to the broadcast controller. How does it communicate with the fabric? Remember, again, the discussion here is around IGMP. So what does that mean? From an IGMP perspective, in multicast environment, IGMP is a pull protocol. See, that's another thing. Pull protocol. What's a pull protocol? The destination is trying to get to the source, which is again, let's say you have a camera trying to send, or a playout system, and you need a multi-viewer that connects to it. The multi-viewer tells the network, give me this source. And then it's trying to pull the source. And then as we are pulling, we basically go up to the fabric until we get to the source. You see, that's how it works in IGMP. That's the multicast. It's a pull mechanism. That's how we set up the trees in multicast. So again, it's just fundamental change is that's why it is better to rely on IGMP for setting up the multicast tree. But we're not too clear. Like, how are we going to do this deterministically? Like, how are we going not to lose packets in all of this? So, the main challenge we have is in PIM. Okay, so and I apologize, we have only 25 minutes, so I skipped some. PIM, you Google it. PIM and IGMP are basically our protocols moving forward. PIM is the protocol independent multicast, which is basically the routing within multicast within the fabric. Very easy, has been active for about 20 years. IGMP is basically the membership, and PIM is routing within the fabric. PIM, the challenge with PIM is that it's not bandwidth aware. So that's the main challenge you have in a fabric environment, is that PIM is not bandwidth aware. What does that mean? What this slide is trying to say is basically, if I'm setting up a path, depending on, I'm relying on PIM, but PIM is not bandwidth aware. So I have to work around that limitation. How do I make PIM bandwidth aware? Otherwise, these links, oh, I was jumping quickly. Okay, so these links, these switches are non-blocking. If I make the links non-blocking, then I have the system non-blocking, I have no loss of packets. That's basically, ultimately. How do I do that? So I need to make PIM bandwidth aware. So that's where in a fabric environment, the fabric is running PIM for protocol management, it's running IGMP for the sources, and I need some sort to make this is bandwidth aware. And that's where you hear in the industry now this ISO 6 and the network controller. Basically to be able to manage bandwidth in a PIM environment. Okay? So in a network controller, with a network controller, with this fabric, you're able to achieve, with a good implementation, bandwidth aware multicast. If you achieve that, then what will happen is that now you have a non-blocking fabric based on open standards. COD switches, you're using open standards. You could have your IT guys troubleshoot this. Again, you are not inventing the wheel. So basically, what we covered is these two topics. How do I build a fabric? How do I make it non-blocking while maintaining using the same protocols? Another change in SIMT from a network perspective. So from a network perspective, another change is, what is the difference? Like, what's SIMT 2110 introducing from a fabric perspective is the scale of multicast. In a SIMT 2022-6, you have a single flow equals single multicast stream. So single multicast stream, single flow, single state of multicast in the switches. In 2110, what you notice is that this flow goes into 18 flows. You have audio, video, and ancillary. What will happen as you pick switches for your fabric? That's another consideration. What is the scale of multicast that switches can do? And why is that? Because multicast has a state in the switch and it uses very expensive TCAM. So make sure as you pick the switches, make sure they have the enough scale. So the scale is typically 16,000 flows, 32,000 flows, 128,000 flows. Very simple. So talk to your switch manufacturer, whoever you pick, and basically make sure that they give you a roadmap for multicast scale, because SIMT 2110 part of challenge is the multicast scale. From a high availability perspective, there's a lot of also discussions on how do I do high availability. So I see two areas. I think there's a talk also I noticed about that. Is basically, do I build a single fabric, or do I do dual fabrics? What do I do? Do I do separate redundant fabrics and do SIMT -7 basically, or do I do a single converged fabric? Our recommendation: start with dual fabric, and that's not because I'm Cisco and I'm trying to sell you more switches. That's maybe part of the reason, but no. To be honest, you see, we are using host mode here. So whether you build a converged fabric or you build a separate fabric, okay? Let's assume you convert these two fabrics into one. Your port count is the same. You see, it's not saving you. When someone comes and tells you, I want to build a single fabric for you, here's what you ask them. What are you saving me? Are you saving me number of ports? Are you going to shave off me this number of leaf switches? If yes, then of course go with them. But they will not be able to. Why? Because it's a host model. Host model meaning whatever bandwidth you are pumping here needs to be equal to the bandwidth going out. So whether he's a converged fabric or no, the same number of ports, 1,000 ports is 1,000 ports. If you divide it by 500 by 500, similar to building a fabric with 1,000. So the idea here, again, as you come through the single fabric versus multiple fabric discussion, challenge that with saying, well, how many number of ports and how do I build it? Our recommendation, start with building 2 fabrics for resilience. That's basically our recommendation summary of this slide. One last thing on SIMT 2110, impact from a fabric perspective. What's the impact? So we spoke about deterministic, so bandwidth-aware multicast. We spoke about multicast scale. We spoke about high availability. One of the last topics is PTP. And there's, again, discussions on PTP. There's a couple of sessions on PTP. We had session before me. The question is, you have to be, from a fabric perspective, you have 3 options. I build a fabric that's not PTP aware. Bad idea. Or I have now to do fabric PTP aware in 2 modes. And I'm showing the first mode here. This is transparent clock. Transparent clock is basically switches who support transparent transparent PTP clock. So, in a transparent clock, what I'm trying to show here is basically if you have 4 endpoints, the grandmaster will receive messages from all these 4 endpoints. So in total, let's assume they receive 8 messages a second. If you scale this to 200 endpoints, they will basically receive, the grandmaster will have to receive and process 200 by 2, 400 messages a second. Let's assume the rate. That's the transparent clock. Boundary clock, on the other hand, you see we have 4 nodes. It's sending messages. The grandmaster receives only 2 messages. If you start scaling it to 200 nodes, the grandmaster, guess what? It will only receive 2 messages. Why is that? Because the switches, the leaves and spines, are basically terminating the PTP and regenerating it. So from a scale perspective, boundary clock scales much better than transparent clock. So overall, without going into the details, if in doubt, go with boundary clock. So unless you pick a vendor, switch vendor that does not support boundary clock, go with boundary clock. So again, if in doubt, go with boundary clock. Forget all these, science discussions, etc. Go with boundary clock if you are in doubt. So let's wrap it together. Again, we are building simple IP fabrics, but these considerations in mind. So I am using the AIMS reference architecture, and let's wrap our discussion together. So in AIMS, they are showing basically primary spine, and primary leaves. So basically, they took the spine leaf that I was showing like this, and they flipped it. Okay, that's the only difference. Same thing, spine leaf, and they are building it separately, not converged fabrics, separate fabrics. Because again, they realize there is no savings. Sorry, there's no savings. So, Wes, I think I did a mistake. Sorry about that. So while we continue, if I put that's perfect. Thank you, Wes. So again, two fabrics, spine leaf. The devices are connected to both of them, right? The grandmaster is connected. You could connect it to the spine. You could connect the grandmaster to the leaf, and you see you have a network controller that manages the bandwidth. So that's basically what we discussed. Is we covered the bandwidth-aware multicast. We covered PTP, and hopefully we can use boundary clock. And we discussed the multicast scale in this. Other than that, this is your typical, traditional spine leaf that we find in any data center nowadays outside of media. Okay? So that's basically the summary of what we discussed as consideration. Identify your endpoints. The key here is identify your endpoints, your IPGs, your playout systems, your servers. What do you connect? Speeds, 10 gig, 25 gig, 40 gig, define that. Once you define that, you can define the type of leafs you use, numbers of them, and where you place them in the facility. Then you need to decide on your PTP, and again, go with boundary clock if in doubt. And then introduce, of course, the PTP grandmaster. as part of the architecture. All right. One last comment. So last time when I presented, there was a question on the 400 gig. So we discussed 10 gig, 25 gig, 40 gig, and 100 gig. In the making right now, in the IEEE, they announced of course, the 400 gig. So vendors, Cisco included, will start releasing 400 gig line cards and 400 gig top-of racks starting December of this year. December of this year onward. And there will be, of course, price reduction as we progress through. So 400 gig optics and 400 gig hardware, it will be available in the next 3-4 months. Will be available, will be shipping. And where do we see the use case for 400 gig? In the spines. So remember the spines? So in this spine layer, 400 gig introduced, and then the uplinks from the leaves to the spines, 400 gig. And now you, of course, you are basically pumping more bandwidth down to the endpoints. All right. So I think we're done. Thank you.